Think about the last time you filled up your tank, charged your car, or replaced a set of tires. Everything is getting more expensive, and cars feel heavier, bulkier, and harder to live with every year. Now here's the strange part. That same car is also safer than any vehicle in history. In a crash, it can absorb massive impact and protect you like a steel cocoon. But what if those two things are directly connected? What if the safety features protecting you are also one of the main reasons simple, efficient, affordable cars keep disappearing? Today, we're breaking down the hidden trade-off between crash protection and efficiency, and why physics is forcing this problem onto every driver. When people think about automotive safety today, they usually picture software features, lane keeping systems, automatic emergency braking, blind spot monitoring, and digital driver assistance. But beneath all of that software sits a much older and far more powerful truth. Real crash protection is built from physics, not code. To protect a human body traveling at highway speeds, a vehicle must manage enormous kinetic energy. That requires three physical systems working together. First, long crumple zones that sacrifice themselves through controlled deformation. Second, reinforcement beams in doors and pillars that resist side impacts. And third, a rigid passenger safety cage that preserves a survivable space even when everything else collapses around it. Every one of these systems adds mass. Reinforced B-pillars, thicker roof rails, stronger door structures, heavier underbody reinforcements, and in electric vehicles, armored battery enclosures. None of this weight is optional if you want 5-star crash ratings. Safety is not a free upgrade. It is a physical commodity paid for in kilograms. And once mass enters the design, it reshapes everything else. Acceleration, braking distance, suspension tuning, tire wear, energy consumption, and drivetrain sizing are all dragged along behind it. This is the structural reason simple, lightweight cars are becoming increasingly impossible to build under modern safety expectations. If we rewind to the 1970s, most passenger vehicles were mechanically simple, structurally thin, and comparatively light. The average vehicle weighed around 4,000 pounds, and during the oil crisis years, manufacturers aggressively stripped mass to meet fuel economy targets, cutting weight by nearly 20% in some segments. But those lighter vehicles performed poorly in serious collisions, especially multi-vehicle crashes involving larger trucks. Public pressure and safety data triggered a cascade of new regulations. Side impact standards demanded door beams, roof crush rules thickened pillars, pedestrian protection reshaped hood structures, airbags and reinforcement zones multiplied. Individually, each regulation added a small amount of material. Together, they rewrote the entire vehicle architecture. Over decades, weight crept upward again and then surpassed previous records. By 2021, the average vehicle reached more than 4,200 pounds. At the same time, the market shifted away from sedans towards SUVs and trucks, which are structurally heavier by design and allowed more regulatory flexibility. What looks like consumer preference is actually reinforced by safety frameworks and compliance economics. Simplicity did not disappear because engineers forgot how to build light cars. It disappeared because survival requirements gradually made thin, minimal structures unacceptable. Here is where the real trade-off becomes unavoidable. Mass is not neutral. It behaves like a multiplier across the entire vehicle system. When you add weight for safety, you do not just pay once, you pay repeatedly. A heavier vehicle requires stronger suspension components to maintain handling stability. Those stronger components add more weight. Increased mass generates more kinetic energy at speed, which forces engineers to install larger brake rotors and calipers to safely dissipate heat. Larger brakes require larger wheels and tires with higher load ratings. Those tires increase rolling resistance and wear faster. To preserve acceleration performance consumers expect, manufacturers must increase motor torque or engine output, which requires larger cooling systems, stronger transmissions, and thicker driveline components. This is known in engineering as mass compounding. Studies estimate that for every kilogram added for safety reinforcement, an additional 0.7 to 1.8 times of weight is added just to support it elsewhere in the system. This is why a seemingly modest safety upgrade can balloon into hundreds of kilograms of total weight increase. Physics does not negotiate. Heavier vehicles require more energy to move, more materials to build, and more resources to maintain. In protecting individuals inside vehicles, we quietly degrade system-wide efficiency.
At this point, many people ask the obvious question: why not simply replace steel with lighter materials? Why not build everything from aluminum or carbon fiber and eliminate the weight problem entirely? The answer is economics and manufacturability. Aluminum is roughly 1/3 the density of steel, but it is several times more expensive, more energy-intensive to produce, and far more sensitive to repair processes. It doesn't behave like steel during impacts and does not tolerate repeated deformation. Repair labor costs for aluminum vehicles routinely increase by over 70% compared to steel-bodied cars. Carbon fiber is even more extreme. It is extraordinarily strong for its weight, but brittle, expensive, difficult to recycle, and nearly impossible to repair after structural damage. That is why it appears in exotic supercars rather than mass-market transportation. Steel continues to dominate safety structures because it offers predictable energy absorption, scalable manufacturing, reasonable cost, and tolerable repair complexity. Advanced high-strength steel allows some thinning, but the underlying mass problem remains. Lightweight materials can reduce weight at the margins, but they introduce cost and repair trade-offs that most consumers and regulators are unwilling to accept.
Electric vehicles intensify this trade-off dramatically. While they eliminate tailpipe emissions, they introduce the heaviest single component ever installed in consumer vehicles, the battery pack. A modern long-range battery can weigh between 1,000 and 3,000 pounds depending on vehicle class. That mass must be structurally isolated, thermally protected, and shielded from impact intrusion. Engineers respond by building reinforced battery cages, thick underbody armor, and additional crash structures. The result is a vehicle that is clean in operation, but heavy in physical footprint. Increased mass raises energy consumption per mile, increases braking distances, accelerates tire particulate pollution, and raises collision lethality for other road users. The environmental benefit of electrification is real, but it is partially offset by the safety-driven mass spiral embedded into battery protection design. This is the central irony of the green transition. To make vehicles safer and cleaner, we are also making them larger, heavier, and structurally more aggressive in the kinetic environment of traffic.
Regulation further amplifies this effect. Fuel economy standards are tied to vehicle footprint, meaning larger vehicles are allowed more relaxed efficiency targets. This creates a structural incentive to increase vehicle size to reduce regulatory burden. Small cars face extremely strict targets that are expensive to meet, while larger vehicles gain compliance flexibility simply by occupying more road space. Manufacturers respond rationally by upsizing platforms across the board. Over time, compact cars grow larger, mid-size cars grow heavier, and truly lightweight vehicles disappear from production lines. At the same time, emissions policy focuses heavily on tailpipe output, while largely ignoring tire and brake particulate pollution, which increases rapidly with mass. The result is a regulatory system that unintentionally rewards heavy designs while penalizing simplicity and efficiency. There is no villain here. There are only incentives colliding with physics and safety goals.
We did not accidentally end up with heavier cars. As a society, we chose structural survivability over systemic efficiency. We optimized vehicles for the worst possible crash scenario, and we subsidized that choice with rising energy consumption, material extraction, and environmental drag. The laws of physics will not bend to policy or marketing. Mass always carries a cost. The question we now face is no longer technical, it is philosophical. Should transportation systems maximizing individual crash survival at all costs? Or should they shift towards system-level safety, energy efficiency, and environmental sustainability? even if that requires rethinking how much protection we demand inside every single vehicle. This is not just a debate about cars. It is a decision about what kind of physical world we are building around ourselves.